Welcome everyone. This is Mamta. I am a senior BI engineer at Sonder, which is an hospitality management company and working in their data and analytics practice. Today with me is Dr. Akshay Goel. He is an MD, is a fellowship trained radiologist with expertise in MRI, abdominal imaging and medical informatics. Dr. Goel is currently working as a senior machine learning scientist at Tempus Labs, where he applies his expertise to advance precision medicine and oncology. Dr. Goel has also won Society of Imaging Informatics Innovation Award for his work on the cloud-based data annotation platform redlearn.ai. Today he will talk about health AI, which is an emerging area of research with promise for significant downstream innovation. So I'll just pass it over to Dr. Akshay.
Okay, great. Yeah, so for anyone who just recently joined, I'm an abdominal imaging radiologist. Currently, I'm a senior machine learning scientist at Tempus Labs, which is a biotech company headquartered in Chicago. We also have offices in New York and California. And today I want to touch upon a topic, optimizing your team for health AI. So this is certainly a broad topic, but some of the things I want to focus on are what are the components of an effective health AI team? I want to visit the concept of data-centric machine learning, which is a term I first encountered during a presentation from Andrew Ng on his Deep Learning AI YouTube channel. I want to touch upon some of the formulations common in healthcare. And finally, I want to go through an example problem with polycystic kidney disease on MRI, which is something I've worked on relatively recently. So when you consider the ideal components of a machine learning team, I think it's clear that there are many diverse core skills at play. Really at the intersection of these skills that you have impactful results. So in the context of health AI, I think some of the things are slightly different, and it's really just the nature of the domain that differentiates health AI. So I want to consider the scenario of a suboptimally integrated domain expert, and just thinking about the different levels of integration, how that could be suboptimal for your work. So in healthcare, there's obviously a wide range of problems. There's medical error, there is optimizing diagnosis, streamlining cost. But even if you take some of the simplest problems in healthcare, when you look at them in a real world setting, they're often not as simple as it might first appear. So one example of thinking about a simple problem, for example, might be detecting blood on a CT head, which is a common radiology scan for someone who comes in, let's say, to the ER with trauma. If you make your objective as a machine learning scientist optimizing accuracy and you miss upon some of the core medical fundamentals, such as optimizing for positive predictive value, negative predictive value, sensitivity, specificity in the context of your disease, you can ultimately end up building something that doesn't really matter and it doesn't translate to clinical medicine. So I think it's important to, in the very beginning, have a good understanding for what's the objective for your model. It's often not always getting a high accuracy. Sometimes I've seen actually when you run a model at scale, for example, in an ER environment, having false positives can be much more damaging than false negatives because they can completely disrupt the clinical workflow. They can actually cost a radiologist more time because they then have to understand, okay, why is this model giving me a false positive? Obviously, no clinician wants to make a error where they disregard a positive result from a model. So you have to take into account how the model plays into a healthcare setting. And I think that is going to help us translate more machine learning models into real world clinical practice. The other thing you have to consider is who are the domain experts? So it's very obvious that you're going to want a clinician who is an expert in the field you're studying. So for example, if you're working in that example with hemorrhage in your brain, you're going to obviously interface with neurologists and neuroradiologists. But your domain experts are also the administrators, the healthcare IT, healthcare workers, really all stakeholders who are going to be interfacing with the result and the consequences of your product. And ideally, you want to have feedback so you understand all of their core needs. That will help you build something that will be successful. At a bare minimum, when you're first building your first version of your model, I think you need deep integration from your clinical expert, especially when it comes to data. So let's say you have a well-integrated domain expert, and by well integration, I essentially mean your machine learning team and your domain experts have convergence in the sense that your machine learning team understands the nuances of the clinical problem, and your clinical experts understand the nuances of your strategy for how you're going about solving that problem, you now need to make sure your domain expert is also heavily integrated with your data. I think ideally your clinical expert should be interfacing with your data in its raw form. If you're doing a lot of model augmentation, they should be able to see what happens to that data after augmentation. They should see that data during annotation to help understand if there are errors being made during that annotation process. And they should be interfacing with model mistakes and error analysis. So this white box here is essentially a gap where that domain expert can't easily interface with data because perhaps that domain expert doesn't have the tech set up on their machine where they can connect to a server and look at data easily. So that might mean your team should be building some optimized interfaces, custom web platforms that can allow a clinician to very nicely provide feedback and interface with that data. I think some of these steps in the beginning can seem pretty painful because they do require engineering support to build, but achieving this early on in your project will pay itself in dividends down the line as you have very high quality data and you have a good understanding for what is the data going into your model. So in summary, deeper integration helps you build something that matters. So now let's take a little segue and look at core radiology data itself, because for the next few slides, we're going to focus on some radiology specific use cases. So on the left here, you have a CT scan with IV contrast. And the purpose of this scan is to diagnose a pulmonary embolus. In this case, actually, the patient does have pulmonary emboli, and you can see some filling defects in that animation, which are positive for pulmonary embolus. And on the right here, you have the radiology report, which is essentially a text representation of a radiologist distilling the visual information in the image acquisition. And the radiologist is also going to take into account any information from the medical record, why the scan was ordered, what the patient's prior imaging showed. So there's really a lot of data at hand when you have a radiology exam. So the reason I want to highlight this slide here is you have to ask yourself, what are you using to supervise your training? So you could either use things from the radiology report, and this is pretty common because if you have a natural language processing algorithm, you can convert the radiology report into categories. For example, you could say this is positive for pulmonary embolus, this is negative for pulmonary embolus, this is positive for some other pathology. Or you could directly annotate pixels with almost like a paintbrush tool in the imaging acquisition itself, and perhaps you then train a segmentation model or an object detection model where you're directly looking for that pathology in pixels. So there are different ways of formulating your labels, and there's no one way that really addresses a problem for every use case. I think you have to consider, okay, what's the cost and benefit of focusing on a radiology report-driven process, a pixel-driven process, perhaps you do a combination. And I think that's really an open, depending on the type of medical problem, but it's something to take into account. The other thing to take into account is when you do have a model or you do see a paper where they derive labels from NLP from a radiology report, you have to realize that there is a ton of very important information in the impression that is not captured in that radiology report. So I know this image here is small. If you wanna see the details, you can reference this article here. But when you look at that impression, it's really a summary of everything going on in that scan. And sometimes it's hard to capture that in your NLP process. So that's something to also keep in mind. So for the next slide, I want you to keep in mind pixel labeling because that's going to require specialized software, right? So now you have to consider how do you interface that pixel labeling software with the rest of your machine learning pipeline. You ideally want to have that software provide outputs that the domain expert can see. Your machine learning models have to be able to consume that. And ideally, your machine learning models should be able to inject model-derived outputs back into your data labeling process so you can have more efficient data annotation. So I think a lot of this highlights the need for specialized infrastructure to build this out. You have a few options. You can build custom software, which really makes sense if you're doing this at a very large scale and you want full customization for what's going to be going into and out of that software. You can leverage a cloud software platform. There are a few early options on the market, but nothing has really taken off in terms of solving all the problems we probably need to solve. Or you could create custom tooling with open source applications. I'll show an example of a open source tool called ITK Snap, which runs on Mac, Windows, and Linux, and it's a pretty powerful tool. But there are a lot of options. The open source community has been pretty active in looking at radiology as a space as a whole. So I now want to shift gears a little bit and introduce this concept of data-centric AI, which was a terminology that I first learned about from Andrew Ng's really nice presentation on his deep learning AI YouTube channel. And this was at the end of March. If you Google for his title, From Model-Centric to Data-Centric AI, it should be easily accessible. So one of the things that Andrew Ng highlights in his presentation is, despite his team having state-of-the-art machine learning scientists with abundant resources, they spend 80% of their time on data preparation. And that means they essentially pick one or two state-of-the-art architectures, they lock their model, they lock a lot of decision-making with their architecture, and then they focus on data quality. And that has been a technique that has helped him get very high-quality results. So I think that's interesting because a lot of researchers can get very glued to the state-of-the-art architectures that are essentially being published on a weekly to monthly basis. But it's important to understand that the data quality is essential for any machine learning problem, and healthcare is obviously no different. So one of the other points he makes in his presentation is the fact that in terms of research and in terms of innovation, 99% of that innovation is happening on the technical aspect in terms of model architecture, training models with less data. And all of these innovations are extremely exciting for myself included, but there isn't quite as much innovation in ensuring model quality. So this is an area that I think is rich for innovation from both a startup perspective, from a research perspective. So I hope to see some more of that in the coming years. Hopefully, some people in this audience can maybe contribute to that. So zooming into his presentation a little bit, there was one example that really stood out to me. And there's this example here where you have two annotators labeling defects in steel. And you can see that while both labelers are correct, you have labeler one being much more granular, and labeler two is higher level. And the question is, if you do this, your model can start to have trouble converging onto an answer. So essentially, having some form of annotation consensus is critical for any machine learning problem. Obviously, your model will learn to reason beyond some random error, but you want to have consensus because it's going to allow you to have a lot more signal in the data you label. And now, instead of a piece of steel, I want you to just picture pathology, right? And pathology tends to be very, very heterogeneous. It's hard to draw a box around a piece of pathology. And I know this image here is quite complex. We have essentially a pancreatic tumor called neuroendocrine tumor. And there's actually involvement of that tumor in the liver. That tumor has involved the spleen. There are areas of normal pancreas in black that are not enhancing as you would expect. So the question is, how would you annotate something like this? And I think that's a question that you need to have at the very beginning of your project. So you form some ground rules, you form consensus. So essentially your signal is consistent and your model can converge to an answer more efficiently. So I now want to explore the different health AI problem types. So I've broken things up into these 4 categories, but you could definitely break things up further. Generally, I see things as being on the easier side of things or on the harder side of things. And by easier, I don't mean that these are easy things to solve. They're just easier in terms of the scale of some of the harder problems. So looking at number one is very popular because essentially we have a lot of examples of effective image classifying models from computer vision in general. And getting the labels for that data is relatively easy. You can just use natural language processing and run it on reports, for example, and you get a lot of labels for pretty cheap. So I think that is a great place to start, and a lot of the research that I've seen published in medical AI is focusing on classifying images or classifying other types of medical data. Quantifying disease is also another direction, which I think is extremely interesting. And that's where instead of just focusing on categorizing a whole image, you say, okay, I want to quantify the specific details of that disease. So how large is that malignancy? How much volume is there in that tumor? perhaps you could assess different classes and compare how those volumes interface with other things, for example, downstream predictions. And I guess that's going into number 4. Number 3 is predicting invasive, expensive features from non-invasive, cheap features. An example of that would be, let's say you have a liver lesion and you want to predict what the pathologist is going to see or what the final DNA, RNA typing results will be on that tissue after biopsy. So anytime you do a biopsy, it's obviously going to be expensive and invasive and come with risks, whereas a radiology scan tends to be cheaper. It's also non-invasive. So predicting invasive, expensive things has a lot of exciting value. There are some papers I've seen published where they can predict the specific gene mutation, or they can predict features that suggest a gene mutation purely from the radiology imaging. But remember that it's not always possible because radiology is one modality and pathology is a completely different modality. When you are, for example, looking at tissue under a microscope, you're really zooming in on something that is less than 1 pixel in scale. And I think that's kind of impressive when you think about it. Whereas radiology is giving you possibly higher level information that you can possibly extract the detailed information that you would derive from pathology or genetics. And number 4 is predicting longitudinal events. I think this is always a hard problem because you are essentially taking a few snapshots in time and you're predicting something that is dynamic. But I think there's a lot of exciting room for exploring number 4 as well. Overall, one takeaway I think is if you are starting off with health AI and you're starting to work on delivering a few promising products, start with 1 and 2, build things that you can actually deploy, and that will set you up nicely for domains 3 and 4. So I want to end with looking at an example of a project I worked on at Cornell during my fellowship, which is measuring polycystic kidney volume. So here is an MRI of a patient. The patient's lying down on their back, and just imagine that their feet are towards you. So this is their right kidney being annotated in red. Their left kidney is going to be annotated in green. This video is sped up by 20x, so no one can really annotate quite this fast. But this shows you kind of the human labor required to annotate data right now with our current tooling. This could definitely be improved. I could see some integration of models with annotation to help propagate things and interpolate things over space. But essentially, the goal here for this project is to predict total kidney volume, because total kidney volume is extremely helpful for tracking the progress of polycystic kidney disease. These patients have autosomal dominant polycystic kidney disease, to be more specific. And it's also very helpful for clinicians who need to make treatment decisions that can have significant side effects for these patients. So that video that I showed there was annotated with ITK Snap. This is a open source software which runs on any platform essentially. The one limitation of this software is that it doesn't naturally integrate with a cloud environment. So you'd have to build custom tooling around it to build. Here are some screenshots I took from the ITK Snap website. So here's an example of brain imaging on the left, and then you have cardiac imaging on the right. Suffice it to say, you can use it for a lot of different types of radiology problems, and it's quite a powerful piece of software. I have no direct connection with ITK. I'm just a big fan. And finally, I want to just give you an overview my experience working on this polycystic kidney disease project, because I think it will hopefully highlight some of the things that any team would be working on in terms of health AI specific to radiology. Obviously, being a radiologist gave me a lot of nice insights into the data as I had interpreted quite a few of these scans during my residency and fellowship. In terms of the data engineering aspect, we had a cohort of our patients, and I used some NLP to help extract the types of images from the MRI exams that would be of highest interest. So that's where I needed some domain knowledge to know which types of images would be valuable for contouring volume. And I also did some data analysis to see which types of images from that MRI exam were most frequently present in our data set. At the end, we ended up annotating 227 MRIs. Initially, we had annotated 60, and then I trained an initial model to see how well we could do. But ultimately, we we went from 60 to 227 to try to push ourselves to get state-of-the-art results. Everything was trained on a single machine. So from our operation standpoint, things were relatively simple. Obviously, for an organization that's possibly attacking multiple problems in parallel, perhaps your data sets are a lot larger, perhaps your problem scope is a lot larger, you would likely need to be working in a cloud environment or some multi-machine environment that you have on premise. And in terms of the model decisions, I really found that the 2D UNet architecture had been used in a lot of healthcare publications. It's one of the gold standard models for segmentation in healthcare. And there was actually an implementation from this repository segmentations model, PyTorch, which utilized EfficientNet, which is a really cutting edge model that optimizes a lot of aspects of your model architecture to achieve high performance with minimal data. So I essentially picked that overall architecture. I locked it to some degree. I did run a lot of experiments to try different parameters with that. But after that, my goal was really optimizing running experiments and making sure we had quality data. I'm essentially going from 60 MRIs to 227 MRIs to get a lot of data for the model to learn. One other really important point in my experience of this project was stratifying data across the and test set. So what I mean by that is essentially if you do a random shuffle across train validation test and you only have, let's say, 60 MRIs or even 200 MRIs, they're going to have some bias in the sense that some of the data in your training set might be larger, some of the data in your validation set might be smaller, and you could have a gap there. So you want to force there to be a stratified split. And I have a blog article that goes into some more detail if you're interested in exploring that further. And essentially, having a strong experimental workflow is important for any project. In this case, I used TensorBoard to track all experiments, and all experiments were essentially run from a configuration file, so I could rerun anything at any point in time, and I had reproducibility. So in terms of our results, just really briefly, we had a pretty impressive dice on the holdout test set. Our prediction of total kidney volume had a pretty small error of 0.5%, but there was a decent amount of variation. So sometimes on smaller cases, small errors can be a large percent of error, especially when you look at things in 3D. But we were pretty happy with these results, and we are optimistic that we can likely use this clinically to add value. And the moment of truth was when we ran the model on holdout, not even holdout data, from other data that was given to us after we trained our model from other institutions, other scanners. We looked at 30 MRIs subjectively. We haven't done a ground truth comparison in terms of calculating dice, but we were pretty happy just looking at the quality of the model. Me, Dr. Prince, and another radiologist inspected 30 cases, and we're pretty excited to see those results. So I think that brings us to time. Happy to take questions, have a discussion. I hope some of the points in this presentation were helpful for anyone interested in health AI. And I look forward to hearing from you. Feel free to also contact me offline.
So I have one question. The whole model that you described, so are you using that in your recent job, like Tempus Labs, or is it like part of the research that you did in Cornell?
Yeah, so a lot of the things I described with Cornell isn't necessarily being directly worked on at Tempus, but the exact details at Tempus are somewhat confidential, so I can't speak to them directly. But that being said, one of the aspects that I worked on, one of the principles for this project was essentially using a relatively simple model gave us pretty strong results, and that was because of our emphasis on data quality, data annotation, and scale. We didn't go to a 3D model, which would theoretically, it should have better results because you're giving the model more context for how to segment things. And optimally, so there's a lot of room for improvement there. But really the question is, if you take that time and you put it into data, you can probably get more out of it.
God, I don't know if it is like confidential, but how do you get data? Like, I understand that in university you get the data from like so many research projects you get chance to do, but when Tempus, like, how do you get the data?
That's a great question. So what happens is typically people, so obviously hospitals have that data in-house, right? Yeah. So they have that data in-house, and there are some, every institution has a different workflow in terms of getting approval to use that data for research. Some institutions are better at that than others. But once you do have that approval, that IRB approval, that gives you that clearance, you typically need hospital IT to help build that cohort for you, and then you can start to explore it. So that's how things were working at Cornell. Some healthcare institutions are further along. In terms of private companies and private organizations, that data typically comes from an exchange with a healthcare partner, where that healthcare partner has some type of business objective or some research objective with the private company, where they say, okay, this is beneficial for us to collaborate with you on the data project. And I think there's a lot of creativity with how those types of relationships are structured. There's definitely not one way of structuring those agreements, as I think there's a lot of different things you can do with that data, essentially. But speaking a little bit from a high level, like how I'm thinking about radiology at Tempus as a whole, or how I'm thinking about it in the precision medicine oncology space, is essentially with radiology, we have untapped signal, right? A human being can look at something and they can qualitatively describe it. They can qualitatively tell me it's worsening. They can tell me it's better. But can we quantitatively do that? Can we do that in a way where we can give much more precise recommendations to patients, to the providers who are taking care of that patients, to pharmaceutical companies who are developing medications? And I think that is really the future of radiology once we start to utilize the mature advances in computer vision, right? So it's very clear that computer vision can tackle a lot of these problems. It's very clear to me that if you have enough data and you're rigorous with how you control that data and you build your model, you can actually get pretty consistent signal. But the question is really, okay, how do we then take that signal to better inform the clinician, to better inform the patient, to better inform pharmaceutical companies that are developing new therapies and running trials? So I hope that answers some questions there.
Yes. So like we have a question from Dave. Like, can you talk a bit about the work? Like, what kind of work, or maybe a research that we are doing in Tempus here?
Mm-hmm. Yeah, so essentially, Tempus, like a lot of biotechnology companies, are essentially exploring the value of imaging data, right? So Tempus has a lot of interesting data that they have, published on their website, so you can definitely take a look. But they're looking at multimodality data from pathology, from genes, from radiology, and essentially, they're very broad. Their scope is very broad, and there are over 1,000 people now working at Tempus. So they're quite sizable, and they're interested in taking data. And I don't want to speak on behalf of Tempus. Obviously, these are my own views. I'm not reflecting Tempus's views as an organization, but they are trying to leverage insights that can help the patient at the end of the day, right? So radiology, given that it has so much rich information in it, our interest is seeing how can we derive value from radiology, either combining it with other modalities, perhaps on its own, things like that.
Got it. So would you recommend any like if someone wants to do research, like any free or publicly available health database where we can go and like just do some research from our own?
Yeah, so there are now quite a few open source data sets, both from the Cancer Imaging Archive in Stanford has recently put out quite a few data sets. So I think from a learning standpoint, and also Kaggle has quite a few competitions. So I think from a learning standpoint, if you're interested in just interfacing with, okay, what does radiology data look like? What are some of the pain points I would have? Maybe let me reproduce some of the work other people have published. I think that's a great place to start. But in terms of if you are a business or you are an organization trying to build a radiology product, I almost think it's more important to start with the clinical question before you start in the data. Because to some degree, the minute you start with a data set, you've kind of started narrowing your scope to that data set, and you start to get tunnel vision that I need to do something with this data set. And I think that on the flip side, it's much healthier to say, okay, what are the types of clinical problems we're going to solve? Maybe what are the easier type problems that we can work on that would have value from a business objective? And then ultimately, once we do achieve that, we can apply that to maybe other data sets. So I think that it's not like what it's, you don't want to do one without the other, essentially, because once you do, remember, interfacing with data is quite expensive. It takes a lot of engineering time to work through the data. Cleaning up the data is non-trivial. I've actually built a lot of custom code that does a lot of data cleanup and structures data so it's much easier for machine learning. So for example, radiology data is stored in a way that is friendly for a clinical picture archiving system, a PAC system. And that data is stored in a way that's not designed for machine learning, right? So you have to take that into account. You have to process the data. In fact, even simple things like sorting slices on a MRI scan, you would think that, okay, you just sort by file name. But that doesn't always work. Sometimes you have to actually look at some of the more detailed encoding information that's in the files. Because this data has been around for 15, 20 years. A lot of those APIs rely on an old school way of doing things.
Got it. Okay. So we have one more question. So like Rohit wants to ask, like, if there is any initiative, like all those institutions have their own data or access to different data sets. So is there any initiative to centralize or consolidate these data and make it more publicly accessible?
Yeah,
Or is it
absolutely.
valuable, or is it? Yeah.
Yeah, absolutely. I mean, being that I'm so interested in this space, I always listen in to talks from other institutions. So Deep Learning AI is a great channel. They have a lot of stuff on their channel. Naturally, they collaborate quite a bit with Stanford. Raised that idea of open sourcing more and more data. One of the drawbacks to things right now is the fact that if the hospital open sources data, they number one need to make sure they have consent for the patients to make sure that that was part of their agreement when they got imaging done at their institution. So they need to make sure from like a medical legal perspective they're cleared. Number two, because things are so litigious, they don't want to make a mistake where they release a piece of information and somehow it can get tracked back to the patient. So anything with your face in it, for example, can be reconstructed in 3D, and that can identify a patient. Also, rare diseases can be tracked to a patient, and there's other ways of having PHI inside the attributes of the data.
Got it. Yeah. Okay. Thank you. I think, yeah, from our side, I think that's it. So thanks again for such an informative talk and answering all our questions. It was
Thank
really
you. Yeah.
helpful, and we really appreciate it.
Thank you so much for hosting me for this.
Thank you. Thanks everyone for joining the talk.